In the last video, we developed the electric field for a uniformly charged ring lying in the XY plane and centered at the origin. And we found that electric field location at a distance z along the z-axis. We're now going to look at some cases where we take and look at the ring very far away, or where the distance above the XY plane is 0. So let's start by, let us look at our result. When z is equal to 0. Now if z is equal to 0, we can see right above that the electric field is equal to 0. So when you put 0 into our result above here, then you get no electric field. Now that's not surprising, because we found earlier that if z was positive, the electric field had pointed up, and if z was negative, the electric field pointed down. So we have this ring, and if you're up here, the electric field's pointing this away, and then it's getting a little smaller. And if you're down in this direction, the electric field is pointing this away, and then it's getting smaller. And if you're right here at z equals 0, there's no electric field. That's much what we expect. The next thing is, well, what if you let r go to 0? Well, if you let r go to 0, then this becomes z squared square rooted. Now that becomes the absolute value of z. So let's consider that. If we take case where let's z be much greater, or at least the absolute value of z, I should say, be much greater than r. So in this case, we need to use the binomial expansion. So here's what we have. We have the electric field, as we said earlier, and we have k, q, z, k hat, and on the bottom, I remind you, we have r squared plus z squared to the 3/2. And what I'm going to do is I'm going to factor out in top and bottom this z. Now I have a z squared. When you take the square root of z squared, you're going to get an absolute value of z. And then I'm cubing that. So I have k, q, z, k hat over the absolute value of z cubed. And then on the bottom here plus 1 plus r over z squared to the 3/2. Now, there is a sign here. If z is negative, this is going to point in the minus k. If z is positive, this is going to put in the positive k. If all we care about for a minute is, let us just consider the magnitude. We can simplify the z over the absolute value of z cubed, since we don't care about the k hat, we don't care about the direction. Then we can cancel one of those z's, and we have z squared, and then we have 1 plus r over z squared to the minus 3/2, which is approximately kq over z squared. And then using the binomial expansion, 1 minus 3/2 times r squared over z squared. Now if we expand that just a little bit, we get that the electric field is kq over z squared minus 3/2 kq r squared over z to the 4th. So it approximately looks like, assuming that I have done what I think I'm supposedly have done correctly, it looks approximately like a point charge, kq over r squared. So if you're very far from the ring looks like a point, and it looks like a point charge. If you want a little better approximation, it's slightly is less than a point charge. They're not quite all aligned up. It has this much, and it goes as 1 over z to the 4th, that correction. Again, here's this r squared, which I said is very small, so this term is going to be very small. So it almost looks like a point charge. All right. Hopefully you can take a basic charge setup, set up the integral, do the calculus, come up with an electric field, and if necessary, do an expansion so that you can see whether or not your result makes sense. For instance, far away it should look like a point charge. That tests your algebra. It also enables us to get formulas that look a lot easier to work out. For instance, right up here, this 1 over z squared, if you think of that roughly constant, this thing is falling, is something that's got like a constant, and then it's got something like a 1 over z squared dependence. Can you get it into a simpler form that you might be able to plot or use for solving real world problems? All right, I'll talk to you in another video.